So in previous work we've been looking at equations of planes and equations of lines in 2 and 3 dimensions, and in this lesson we're going to look at the intersection of lines and planes, or in fact how lines and planes interact with each other, because they don't always have to intersect. In fact, there are 3 possibilities, and I'll show them for you now. A line could intersect with a plane, of course, so a line could pass through a plane, as in this example here, and if that's the case there will be a point of intersection with the line and the plane. In other words, the line and the plane occupy the same space. The second possibility is that a line and a plane could be parallel to one another. So here's an example of what that might look like. There's a line, there's a plane, they're parallel to each other. They're not going to intersect. And the third possibility is that the line and the plane are parallel, but actually the line lies in the plane. So that would look like this, and that would give us an interesting answer in terms of the point or the points of intersection. So previously we've seen the equations of lines and planes, and we will be using the format that's most appropriate to solve this problem. So we're going to illustrate this with an example here. In this example I've got an equation of a plane in Cartesian form and an equation of a line in Cartesian form, and I'd like to look at and see which possibility it is. So which of those 3 is it? Do they intersect? Are they parallel? And if they are parallel, are they actually is the line in the plane? Now then, we've got here the Cartesian form of a line, and that's not always the most helpful to work with. So what we're going to do first of all is convert that into parametric form, and then actually we might even consider the vector form to think about the direction of the line. So let's do that conversion. So minus x is equal to lambda. It's also lambda going to be equal to y minus 5 over 2, and of course 2z minus 8 is going to be equal to lambda as well. So let's do a quick rearrangement of those and have them in the form that I want. So x is equal to 0 minus lambda, y is equal to 5 plus 2 lambda, and then z is equal to 8 plus lambda over 2, just by rearranging those. And the reason I put them in that form there is it's now easy to convert that into the vector form, and the order there hopefully 8 over 2 for the position of 0, 5, 4, a point on that line. So the direction minus 1, 2 and 1/2. So we've got a line that has got 0, 5, 4 as a point on it, and the direction of it is minus 1, 2 1/2. Now, as we've seen before, we can have numerous forms of this line. If you can find another point that is on that line, you could give me another equation that is correct, that defines that line. And similarly, I could have a multiple of this, and that's what I would like to change a little bit here. I'm not so keen on having a half in there. So if I just double that direction vector, then I will get rid of that fraction. So I could rewrite my equation x, y, z is equal to 0, 5, 4. Let's change my parameter here so I'm not going to get confused with what I've written. I think it's the same. Let's write that as 2, 4 and 1. So that's just a different equation of the same line, and that's just going to be a little bit easier to work with. So let's just consider for a moment these 2 possibilities. For these 2 cases, the line is parallel to the plane, and so what we want to do here is consider the direction of the plane and the direction of the line. So here might be my plane, here might be my line. They're parallel to one another, so what do we know about them? Well, here's the normal to the plane, and that's what we have in our definition of our Cartesian form. We can get that quite easily. If the plane and the line are parallel to one another, then those two lines there are going to be perpendicular. So that's something that we can easily work with. So the equation of our plane in Cartesian form is this one here, and the vector form that we found for the line is this one here. I just noticed I made a mistake there. It should have been -2. Of course, there you probably noticed that. This means what? Well, the direction of this plane, or the direction of the normal for this plane, is going to be 3 - 1, 1. And the direction of this plane, this line, is -2, 4, 1. If they're perpendicular to one another, then the dot product there would be equal to 0. So we can check that. -2, 4, 1 dot 3 - 1, 1. What does that give us? Well, it's certainly not equal to 0. So the plane and line are not parallel. Well, if they're not parallel, then the line isn't in the plane either, therefore the line and the plane meet at a point. And our job now is to try and find that point. So what we're going to do then is try to find the point of intersection of this line with this plane. Now if the two intersect, then that means there's a point that is common to both the line and the plane. That means for a value of mu, they will be the same. So what we're going to try and do is find which value of mu will make the x coordinate and y coordinate and z coordinate the same for them both. So x is equal to -2 mu, y is equal to 5 plus 4 mu, and z is equal to 4 plus mu. So what we're going to do is find the value of mu that will give us the equation of this plane. In other words, 3 lots of x minus y plus z is equal to 8. And all we've got to do now is solve that and find the value of mu. So normally you can see if you've got these right, because generally the people who set the questions are clever enough to make the values that you find nice whole numbers or perhaps rational numbers that are not too tricky to work with, and that's certainly the case with this one. That gives us a value of mu to be equal to 1. So that's the value of mu that makes the x coordinates, the y coordinates and the z coordinates in the line the same as the plane. So we just got to work out what they are. So we know that the x coordinate is minus 2 mu, so that's 2. We know that the y coordinate is 5 plus 4 mu, so that is 1. And we know that the z coordinate is 4 plus mu, so that's 3. So there's a point of intersection at 2, 1, 3. And that's how we consider the intersection of a line and a plane.